My name is Primoz Kolman. I'm a customer success engineer at ThousandEyes, a network intelligence company. And I would like to guide you in the next 50 minutes through some of the major outages, network and service outages that we have observed in 2015. We'll start with the level 3 route leak that occurred on June the 12th, 2015. And what happened is that around 8:43 UTC, Telekom Malaysia announced a large portion of the global routing table. Level 3, which is, as we know, one of the biggest tier 1 providers in the world, accepted these routes and was just advertising those routes to the level 3 peers. What happened is those routes attracted new traffic that followed the routes into the level 3 and Telekom Malaysia's network, which flooded all the major level 3 peering points around the globe. Obviously, that affected a large number of different global services, such as Google, Microsoft, LinkedIn, etc., etc. In the Europe, peering points such as London, Amsterdam, and Frankfurt became flooded with the traffic. So first of all, we checked out the route visualization to see what happened with the routing table. In this case, we have a Royal Bank of Scotland digital website, which before the route leak, on the left side, we have a London BGP monitor, which is peering with the level 3 autonomous system. And before the route leak, the best advertised path was through the level 3 AS through Prolexic AS, which is the primary upstream provider for the Royal Bank of Scotland, to the RBSG network. After Telekom Malaysia started to advertise the global routing table into level 3, the path got diverted, and going from London to the Royal Bank of Scotland digital website, the optimal advertised path was through the Telekom Malaysia, through the autonomous system of Hong Kong Internet Exchange, back to Prolexic, and to Royal Bank of Scotland. So this is how the AS path changed. But what happened with the packets? On this slide, we have 8 agents that we use to perform measurements in the UK. And in the middle, you have 5 agents which are presented with the green note. It means they had no problem connecting with the Royal Bank of Scotland digital website. Why? Because none of these were using level 3 as the primary upstream provider. So you can see all the paths go nicely into the Prolexic network. They all go through this common node, blackhole.prolexic.com, and to the Royal Bank of Scotland digital website. However, on the top, we have 2 agents, one in Country, one in Maidenhead, that are placed in a data center that uses level 3 as the primary upstream provider. What happened here is that as soon as they get to the level 3's point of presence, in this case in London, we see a huge forwarding loss up to 86%. A few packets actually made it through on the right side, where they were black-holed in the level 3 network. There's an interesting path going down there, actually reaching the target after some 15-20 hops, which means there was some kind of a routing loop. The packets got looped, but eventually found their way to the Royal Bank of Scotland digital website. At the bottom, we have a Northampton agent, which uses Cogent as the upstream provider, and you can see that between the last Cogent node and the first level 3 node down there, there was a huge saturation of the link. A lot of packets got lost, so we had like 75% forwarding loss. Even those few packets that made it through were then discarded in the level 3's network. What was interesting about the level 3 route leak is that there was also collateral damage. In this case, we have a Capital One website which uses level 3 as the upstream provider, and the advertised AS path for the capital 1 did not change. So there were no changes in the routing table. However, we have still seen a huge drop in their website availability, a huge increase of the packet loss. And what's more interesting, it didn't just last for 2 hours. Because after 2 hours, level 3 stopped accepting the Malaysia Telecom routes. But the ripple effect lasted for a couple of hours after that. Even a couple of hours after the route leak, we've seen low availability, high packet loss, and so on. So this is a nice showcase that shows you how a very simple route leak can affect the availability of the sites around the world when we're talking about a provider such as level 3. Second case is Amazon Web Services route leak, which occurred on July the 1st. It lasted just a bit under 1 hour, and what happened is that a number of networks around the world were not able to reach Amazon or Amazon Web Services hosted services. We have a number of customers that use AWS to host their services, so we got multiple internal alerts notifying us that there's an impact and a packet loss, and we have identified that the packet loss is happening in 2 very specific networks. We have then found out that the loss was caused by a route leak from the XLX, which is a data center provider in Boston. And what they did was basically they advertised around 60 AWS prefixes into the Hibernia, Netherlands network. So when we looked at one of the, we monitor a lot of services. One of those that we often use is Tinder. And when we looked at the path visualization, where the packets are going, we found out that suddenly there were new nodes in the path of the packets from Hibernia, Netherlands network. And what's more, in Hibernia, Netherlands network, there's a node that's dropping all the packets. We immediately suspected a route leak, and when we looked at BGP route visualization, in this case from our London BGP monitor, we noticed that a normal path which went through Claranet, through level 3 directly to Amazon was now changed. And the new best path was through Claranet, through Hibernia, Netherlands, through XLX, so this is this Boston DC provider, and back to Amazon. And when we looked into the raw BGP data, we've noticed that there was just one single update sent from the XLX into the Hibernia, Netherlands network that diverted traffic for over 60 prefixes belonging to AWS through their network. They even prepended their own AS 4 times, but that didn't help. That this network would not be advertised as the best possible choice by Hibernia, Netherlands network to their peers. Third outage that we have is UltraDNS outage that occurred in October 15. It was a DNS outage that lasted more than 2 hours when multiple UltraDNS name servers were unreachable or really slow to reach. Why do we care about UltraDNS? Because they're a major DNS service provider to services such as Netflix, Expedia, major banks, Uber, also Pornhub. And Neustar, the company behind the UltraDNS, they initially claimed they were under DDoS attack. Then they changed their position. They claimed it was a server issue on the East Coast. And in the end, they tweeted it's a management configuration error. So we were really interested in seeing what was going on. UltraDNS has presence in around 30 data centers around the world. And what we immediately found out is, if you look at the map, that this was a very region-specific problem. The problem was between Denver in US and Moscow on the other side, while other regions were largely unaffected. The way UltraDNS is hosting domains is that each domain uses 6 of their DNS servers, which are anycasted from usually different data centers. And as you can see, we have two very distinctive gaps in the availability. First gap lasted 1 hour, and it was availability gap that was seen both in Eastern US as well as in Europe. After about an hour, the availability in Europe returned, while the Eastern US still had problems reaching those servers, and after 2 hours, the availability went back to 100%. So we've taken a look to a very specific DNS server, pDNS5 of the UltraDNS. On the left side, you can see different agents that we use from around the world. On the right side, you can see the IP of this DNS server. The node on the right side is not a single node. Because the address is anycasted, it's actually present in multiple data centers around the world, which you can identify if you just move to the node left from the DNS server node. You can see we have 7 different nodes. And you can see that the biggest, the only node that has problems, which is having heavy forwarding loss, is the Amsterdam, Netherlands node. We have noticed that they were having problems in about two-thirds of the data centers around the world. In Europe, that was Amsterdam, it was London, it was Frankfurt, while in Madrid and Paris, they had no problems at all. You can see that Madrid, Spain is green, and the path is going directly to the DNS server, so no problems there. We use the same agents to look at the pDNS3 server, and pDNS3 server for most of the Europe is anycasted from Frankfurt. And again, we have the same problem here. So based on that, we have concluded that this was most likely a configuration error on their side. Why? If there would be a DDoS attack, we would most likely see, first of all, it's really hard to regionally target DDoS attack for any cast service. And second of all, we would usually see different packet loss at different nodes. I invite you, we have a booth just outside on the left. We have a really nice example of Halifax DDoS that happened 11 days ago, and we can discuss it more. It's a more complex issue, and it usually produces packet loss at multiple nodes in the path. So the real question here is how many and how much were the customers affected? Because first of all, we have these recursive resolvers that most of the end users use. Then we have DNS caching, etc., etc. So what we did during the outage is, for one of the customers, we have checked how their domain zionsbank.com a record is resolved from 2010 open resolvers around the world. The A record has a TTL of 300, so it's a pretty short TTL domain. And during the outage, we've noticed that the availability of the domain around the world was around 63.7%. You can also see that in which regions it was focused. So red means availability 60 or 50 or less percent, while green means 90 and more. As you can see, Paris, Madrid, everything's fine. The other parts, US, the Eastern and Central Europe had huge availability problems. Okay, just a quick one to finish the presentation with. Brazil blocks WhatsApp. That happened in December 17th, not so long ago. It's not a very interesting technical problem, but it's an interesting political problem, I would say. Brazil was a net neutrality champion in 2013, in 2014, but they kind of reversed their position in 2015. WhatsApp has 93 million users in Brazil, and that's a country of 200 million people, which means pretty much every second Brazilian uses WhatsApp. And you can imagine the telcos lobby against WhatsApp as much as they can. After WhatsApp refused turning some of the data in one of their investigations, court ordered a 48-hour blackout, and users and social media and news sites just went nuts. So after 12 hours, they kind of reversed that decision, decided they will induce a penalty fine or something like that to WhatsApp. What's more interesting is that users just found a different way. There's a service, messaging service called Telegram, which is similar to WhatsApp, and they claim that just overnight they've got 1 million new users from Brazil. and they claim that in the first day alone, they got 5 million new users. So users will always find a way. The way the blackout looked like from our perspective is pretty similar. You have different agents around the world, which can all find a path to the WhatsApp servers. On the other hand, the agent that we have in Sao Paulo, Brazil, got all the traffic blocked at some point in Brazil network. And if you look on the top, that's an availability graph, 100% availability from all around the world, except, sorry, that's the packet loss graph, except in Brazil, where we have 100% packet loss. All the packets were dropped somewhere in Brazil. Thank you. Just one last thing. I would like to invite you to click on the live share links that we have in the presentation. They will get you the same data that we used to make the presentation. You can play with the data, get to your own conclusions. If you have any questions, find me outside and we can discuss it further. Thank you.
Thank you, Primoz.